Hello dear students, in today's class, let us try to calculate the moment of inertia of a thin uniform rod. So we already have a basic idea about moment of inertia. We had defined the equation for moment of inertia as I equal to summation over all the points inside the rigid body, mass of each of the points into Ri square, where Ri is the perpendicular distance from the axis of rotation up to the point which is considered. In the case of continuous mass distributions, this summation will be changed to integration. If the mass points are discrete, we could actually sum over all the mass elements. Otherwise, we will have to do integration. In the case of a rod, we will use integration method because this is a continuous mass distribution from one end of the rod until the other end. So in this unit, we will look into the moment of inertia of the rod about two specific axes. First, we will try to calculate the moment of inertia about an axis passing through the center of the rod and perpendicular to its length. So you can imagine this axis like this. It is passing through the center of the rod, exactly through the middle, and it is perpendicular to the length of the rod. So this is the length of the rod and it is perpendicular to that. The axis is perpendicular to that. And secondly, we will try to calculate the moment of inertia of the same rod about another axis, and that axis passes through the end of the rod, one end of the rod. So these two are the cases which we are going to look into. First, let us calculate the moment of inertia of the rod about this axis passing through the center of the rod and perpendicular to its length. In order to find that, we consider that the axis is located at the origin, so that one end of the rod can be assumed to be located at minus L by 2 and the other end of the rod is located at L by 2. So the total length of this rod is L by 2 minus L by 2, which is L. So L by 2 and L by 2 are the two halves of this rod, towards the left and towards the right. The axis is located at the origin. So it is easy to do the mathematical part in this way. That is why we choose the system like this. So both the lengths are L by 2. Now in order to calculate the moment of inertia, we will have to do integration. Integration over mass into x square, where x is the distance from the axis up to each of the small mass units, small elements. So in order to calculate mass of each of the small elements situated at various lengths from the axis, we need to consider a specific term. In this case, it is the mass per unit length. So let us define mass per unit length as mass by length of the rod. It actually indicates the mass of the rod per unit length, say 1 centimeter or 1 millimeter or 1 meter. So per unit length of the rod, what is the mass of this rod? That is indicated by this term. So it is defined as rho in this case, linear mass density. We could call it linear mass density. So it is mass by length. Now coming to the calculation of moment of inertia, let us try to find out the moment of inertia contributed by a small mass element at a distance x from the axis. Its length is dx. Since it is very small, we could call the length of this mass element as dx. So what will be its moment of inertia? So we do not have to do integration or summation in this case to calculate the moment of inertia of a single mass element. It will be simply its mass into distance square. Now what is its mass? We know the mass, linear mass density, which is defined as rho. Its length is dx. So its mass, the mass of the small element, will be rho into dx. That is how you find the mass, right? If you know the mass per unit length, multiply by the length of the element to get the mass of the element. So the mass of this small element that we have considered is simply rho into dx. Rho is the mass per unit length and dx is the length of the element. Now to calculate its moment of inertia, so the moment of inertia of this small element about the considered axis. Is equal to rho into dx, which is the mass of the small mass element, multiplied by x square. Rho dx into x square. So this is the moment of inertia due to a single element present here. A rod is comprised of a large number of these small elements present from one end until the next end continuously. So here we will have one small element followed by another one and so on. So this is a continuous distribution of mass. So to find out the total moment of inertia of the rod, we will have to integrate this term over the whole length. So when we integrate, we can see there are mass elements, small elements present to the left side of the rod and present towards the right side of the rod. So let us do this integration in small parts. So first we will have to integrate from minus L by 2 up to 0, which means from this end of the rod until the middle, the moment of inertia due to each of the mass elements. And then we will have to add the moment of inertia due to the right arm of this rod, which is integral 0 to L by 2 rho dx into x square. The total moment of inertia will be the sum of both these terms. So let us calculate this part. It is equal to minus L by 2 up to 0 rho dx into x square plus 0 up to L by 2 rho dx into x square. Here the first term is contributed by the moment of inertia due to the left arm towards the negative side, and this is the moment of inertia due to the right arm of the rod. So this is equal to rho into, we know integral x square dx is x cube by 3 from minus L by 2 up to 0 plus rho is a constant, that is why we are taking it out of the integration, into again x cube by 3 from 0 up to L by 2. Now let us substitute for these values. Rho from 0 by 3 minus L cube by 8 divided by 3 plus rho into L cube by 8 divided by 3 minus 0. L cube by 8 is L by 2 whole cube. So this is equal to rho by 3 into L cube by 8 plus again rho by 3 into L cube by 8, which is 2 times rho by 3 into L cube by 8. So this is simply is equal to rho L cube by 12. Now we know rho into L is the total mass of the body. We defined rho as m by L. That means rho into L is the total mass of the body. So instead of a single rho L, you can substitute mass. The remaining term is L square divided by 12. So the moment of inertia of the rod about an axis passing through the center and perpendicular to the length of the rod is given by I equal to ml square by 12. Now having obtained this equation for moment of inertia through the first axis, let us try to find out the moment of inertia about the second axis. So this axis passes through the end of the rod, and as we can see, the second axis we are considering is actually parallel to the first one. So suppose this is Rx and this is r dash s dash. So these two axes are parallel and the moment of inertia about the first axis is known. It is ml square by 12. And due to the symmetry of the rod, it is already known that the center of mass of this rod will be situated at the middle point, which is ICM, which is equal to ml square by 12. Now to calculate the moment of inertia of the axis r dash s dash, we may make use of the perpendicular axis theorem. Sorry, the parallel axis theorem. So according to the parallel axis theorem, the moment of inertia I will be equal to ICM plus mass multiplied by distance between the axis square. Since these axes are situated at a distance of L by 2 from each other, D is equal to L by 2 in this case. So if you look at this picture, the first axis is situated at the center of mass and the second axis is situated at the end of the rod. So the distance between them is L by 2 in this case. So making use of the parallel axis theorem, we may write I equal to ml square by 12, which is ICM, plus mass into L by 2 the whole square. So this is equal to ml square by 12 plus ml square by 4, which is equal to ml square by 3. So you do it like this: 4 ml square plus 12 ml square divided by 12 into 4, which is 48. So that is 16 ml square by 48, which is ml square by 3. So we have calculated the moment of inertia of the rod about two different axes. In the first case, we obtained moment of inertia as ml square by 12, which also happens to be the ICM when the axis is chosen like this. Axis is perpendicular to the length of the rod. In the second case, moment of inertia is equal to ml square by 3. And which moment of inertia is greater? You can see that the second moment of inertia has a greater value. That means it will be more difficult for you to rotate a rod by fixing an axis at the end of the rod than fixing an axis inside through the center of mass. So that is the concept about moment of inertia. I hope the calculation of moment of inertia in the case of the rod is clear for you. Thank you.